series.
Thanks for inviting me. I'm very happy to speak here. So I want to discuss an ongoing work with Florian Naef, who is also in the audience. And this is about understanding the topological field theory behind string topology and better understanding the kind of structures that are there. Let me begin with something relatively simple. So let's say you have a closed oriented manifold of dimension d, let's say. Then on homology, you have an intersection product. So it shifts the degree by d. And for the intersection product, you can ask, well, is this actually homotopy-invariant? So the first question you should ask, is the dimension homotopy-invariant? Because then without that, the question doesn't even make sense because there's a shift. Well, the dimension indeed is homotopy-invariant. That's relatively easy to see using Poincare duality. Now, for non-closed, note that for non-closed manifold, this is not true. So for instance, Rn is homotopy equivalent to the point, but they have different dimensions. Okay. And the second fact is that actually the intersection product is homotopy-invariant. So if you have a homotopy equivalence of closed oriented manifolds, then it intertwines the intersection product. Again, that shouldn't be obvious to you just because intersection product involves, I don't know, intersecting some kind of submanifolds. And of course, homotopy equivalence doesn't have to be a homomorphism or a diffeomorphism, even better. Okay, so the claim is that the intersection product is homotopy-invariant, possibly up to a sign. The sign is coming from the orientation. Okay, and so the project with Florian is trying to answer the following questions. So there's a lift of these of the intersection product to the loop space. So there's the so-called string topology operations. So there are various versions, and I'll talk about those later. But basically, it's homology of the free loop space, possibly as one equivariant, possibly relative to constant loops. So there are some structures related to intersection theory on the loop space. And the first question is, are these string topology operations actually homotopy-invariant? So the same question as above. If you have a homotopy equivalence of oriented manifolds, do those intertwine string topology operations? Or maybe string topology sees more than just the homotopy type. And the second question is, can you construct an extended, possibly up to homotopy two-dimensional TFT, which has these string topology operations? And so we'll also discuss those. There will be compactified string topology operations, and what's the TFT meaning of those? Okay, so these are the motivating questions for today. But let me begin with the old story of the Golem Bracket. So let's say you have an oriented surface, and you consider loops inside of the surface. So let's look at the free vector space on homotopy classes of loops in sigma. Then this vector space has a Lie bracket called the Golem Bracket. So basically, if you have two loops, generically they will intersect just because they're one-dimensional submanifolds. Let's say you have a bunch of intersection points. Then what you're going to do is you're going to sum over intersection points with certain signs coming from so you're basically doing sign intersection number. And then you just compose them at the intersection points. So here I have an example. You have loop alpha and loop beta on some surface. You should imagine that this is not on a plane. Otherwise, it's just silly because you can separate them. But maybe there's some genus somewhere in the middle of the loops. And so the bracket is going to be the sum over intersection points. So there are two of them in the picture, the top and the bottom one. And then you just compose them So what I've drawn is I kind of separate them a little bit at the intersection point and composed at that point. So you have sum of these two loops, or the difference in this case. And the claim proposition of Goldman is that this is actually a Lie bracket. So it's antisymmetric, which is relatively easy to see just because you're doing sign intersections. And maybe a little bit more difficult is Jacobi identity. Okay. Let me explain the motivation for the Golem bracket. So the reason he introduced actually this bracket. Let's say you have a Lie group. So maybe you work with complex Lie groups. You could work with real Lie groups. I'll just for simplicity work with complex Lie groups. So for instance, you look at n by n matrices with complex entries with determinant non-zero. So JLNC. And suppose this Lie group has a non-degenerate pairing on the Lie algebra. So for instance, for JLN, this would be the trace pairing. Then you can consider the space called the character variety, denoted by log G of sigma. So sigma is again my oriented surface. And there are various ways of presenting what this means. So one way to say what the character variety is to say, well, it's the variety of characters. So you look at homomorphisms from the fundamental group of sigma into G, and then you mod out by conjugation. Okay. Another way, slightly more topological, is to say it's a space which parameterizes local systems, G local systems on sigma. And yet another way is to say that it parameterizes flat G bundles. So principal G bundles with a flat connection on sigma. They're all going to give you the same set. Okay, and this is a manifold, and well, generically. And this manifold is going to carry a Poisson structure. So basically, there's a construction due to a Tft Approach of the Poisson structure on the modular space of flat G bundles. Okay, so you have this character variety, and it has a Poisson structure. So how does this Poisson structure relate to the Golem bracket? And again, let me concentrate on the GLN case. So I introduced this vector space of loops. I called it frag G. So it has nothing to do with the capital G, which is GLN in this case. But okay, so if you have a loop, you can actually obtain a function on the character variety. If your group is actually algebraic, you get an algebraic variety, and this function is going to be an algebraic function. In general, it's just going to be a smooth function if you're working with the groups. And the function is obtained in the following way. If you have a loop, you can consider, if you think about flat G bundle, you can consider the monodromy around this loop. This is going to give you an element of G, and then you apply the trace. Or if you think about this presentation as just homomorphisms from pi1, if you have a loop, you get an element of G, and then just take its trace. And of course, it's G invariant. Okay, so there's this natural linear map, and the claim of Goldman is that this map is actually a map of Lie algebras. So it intertwines the Golem bracket on G and the Tft Poisson structure, a Tft Poisson bracket on the algebra functions. Okay.
Pavel, do you know if this map is 1-to-1?
No, it's far from 1-to-1. So you should think about the left-hand side as kind of, sorry, yeah. If you just ask about, you can look at something silly like n equals to 1. I would imagine it has a huge kernel in that case. So basically, you might have accidental relations between your loops. So one way to think about the left-hand side, so free loops, it's something like the version of the right-hand side when n is infinite. But for any finite n, there might be accidental relations. And I think for n equals to 1, there'll be relations.
Thank you.
That's a good question. Okay. Now let me introduce one more operation due to Turaev. And this is an operation on the same space. So again, I'm still considering loops inside of sigma. Okay, so suppose you have a loop inside of sigma, and maybe it has a self-intersection point. So like drawn here, so you have a single loop which looks like figure 8. And the single loop is, well, it's consists of two loops in this case. You have a loop alpha on the left, a loop beta on the right. And you can define an operation from G to G tensor G, which basically splits this figure 8 at the intersection point. So you can define this delta of this figure 8 is going to be alpha tensor beta minus beta tensor alpha. Again, there's a signed, there's some signs coming from the intersection and how exactly you separate the two loops. Okay. Now, what sort of algebraic structures or what sort of algebraic identities this operation satisfies? So first of all, let's look at the case where you mod out by constant loops. So maybe I assume that sigma is connected in this case, so you have just one-dimensional space of constant loops inside of G. Then the claim is that this operation is actually a Lie cobracket. So it's antisymmetric, as you see in this example, and it satisfies a co-Jacobi identity. And something peculiar is, so how can you deal, so I'll explain in a second why you have to mod out by constant loops. But something interesting you can do is, well, instead of modding out by constant loops, you can assume that sigma has a non-vanishing vector field. And one way to think about the non-vanishing vector field is to say that it's a trivialization of the Euler class. So if you have a non-vanishing vector fields, of course, the Euler characteristic is 0. But I'm thinking a little bit homotopically, so you have a cochain which represents the Euler class, and I want to trivialize this cochain. And a trivialization of this cochain is what I'll call an Euler structure. So this is a notion due to Turaev. And so basically, if you have an Euler structure, maybe you have a non-vanishing vector field, or maybe you have some combinatorial way of presenting that, then you can actually define this cobracket on all loops. You don't have to mod out by constant loops. And let me explain what the problem is. So suppose you have any loop, and you imagine applying the Rademacher 1 move. So you have a loop, and it develops an extra little loop at some point. So on the left, you didn't have any intersection point, self-intersections. On the right, you developed one more self-intersection. So of course, delta on the left will be just 0. On the right, you'll pick up a constant loop. So that's the problem, why a priori this operation is not well-defined on all loops without modding out by constant loops. And the way non-vanishing vector field fixes this problem is you can look at loops which have a binding number 0 with respect to that vector field. Okay. And so in either of those two situations, either if you look at loops mod constant loops, or you choose an Euler structure, you obtain a Lie algebra. So you have the Golem bracket and derive cobracket. Okay. So are there any questions so far?
So you need the Euler class to actually be 0.
For the second version, yes. If you mod out by constant loops, you don't have to choose an Euler structure. So you don't.
Okay.
If the Euler characteristic is non-zero, the second version doesn't work.
Okay.
But the first version
thanks.
works fine.
Okay, thanks.
Okay. So now these operations, this Golem bracket and derive cobracket, were generalized by Chas and Sullivan to higher dimensions. So far I'm discussing.
Sorry, for a surface, do you ever get something that has Euler characteristic 0 aside from, let's say, sphere?
A sphere has Euler characteristic 2.
I'm sorry, aside from the torus.
Well, let's see.
The Euler characteristic is 2 minus 2g.
Well, so the surface here is not necessarily closed.
Oh, okay, okay.
Yeah. So yeah, maybe let me not say what I assume about the behavior at the boundary of the vector field.
Okay, that no big deal. I just want to.
Yeah. Okay. Yeah. So the idea of string topology operations is to generalize this picture to higher dimensions. So replace a surface by a D manifold. Okay. So suppose you have a closed oriented D manifold. Then you have the following string topology operations on the homology of the free loop space. First of all, you have this thing called the string product or the loop product. It looks exactly like an intersection product, but on the loop space. And it's kind of a lift of the intersection product to the loop space. Then there's another operation closely related to the string product called the string bracket. It's an operation 1 degree higher. It's also a binary operation, and together the string product and string bracket form what's called the Gerstenhaber algebra. So the string product is graded commutative, the string bracket is the Lie bracket, and together they satisfy a kind of Leibniz identity, or graded Leibniz. There's also the BV operator, which basically comes from rotating the loops. So there's an S1 action on the loop space. This induces a homotopy S1 action on homology. So it increases the degree by 1. And again, the first 3 operations form what's called a BV algebra. BV stands for Batal-Minkowski. And finally, so the first 3 operations are just vanilla string topology operations. You can imagine other operations from other kinds of Riemann surfaces. But there's another class of operations which are called compactified string topology operations. So I'm not explaining here the precise construction and also why I call them compactified, but okay, so there's another class of operations, and one example of this operation is called the string coproduct. So this is due to Goreski-Hingston and more recently Hingston-Wall. And so this is going to be a lift of this derived cobracket. And again, there are 2 versions, just like for the derived cobracket. First, if you have an Euler structure, so a trivialization of the Euler class, then you can just define a cobracket on the homology of the free loop space with some shifts. And then if you don't choose an Euler structure, you can define a cobracket on the homology of the loop space relative to base loop, relative to constant loops. Okay, so this is completely parallel to this theorem of Tareyev, how you can construct a Tareyev cobracket. And indeed, if you look at the case of a surface, so the manifold is two-dimensional, and you look at a Swan equivariant homology of the free loop space of a surface, then this is just going to give you the same vector space as before. So the free vector space on homotopy classes of free loops in sigma. And then the induced bracket here will be the Golem bracket, and the string co-bracket, which is a variant of the string coproduct, will coincide with Tareyev cobracket. Okay, so again, you should think about these operations as higher dimensional versions of the Golem Tareyev operations.
So the Levi algebra also has a higher dimensional version, right? In this one, equivariant homology of the free loop space.
Right. Yeah. So I didn't write it separately, but yes. So there's a string bracket, there's a string co-bracket, and together they form. If you look at the homology of the loop space relative to base loops, and you look at the Swan equivariant homology, then you get an involutive Levi algebra in this case. There's also a lot of work on extending to chain level. So there's a IBL infinity structure. Yeah, so there's been quite a lot of work on string topology. Okay, algebraic sites of string topology. Okay, so let me mention, so far, so here I started with the manifold. And I said, well, you have these operations on the homology of the free loop space, and these operations involve some geometry, so they involve intersection theory. Now, in the case when the manifold is simply connected, and you're working over the reals or over the rationals, you can have an algebraic model of the string topology operations in terms of a Frobenius algebra structure on the cohomology of the manifold. So basically, if you look at this Frobenius algebra cohomology of the manifold, and you take its Hochschild homology, this is going to be cohomology of the free loop space.
Pavel, can I say something here?
Yep.
I think you might want to say, you want to remember the chain level structure of the cohomology, right? Technically speaking, what you just said, it only holds for like formal manifolds,
right?
Right. So it's really in terms of a lift of the commutative Frobenius algebra structure to the chain level. But in order to recover the free loop space, in terms of Hochschild models, you need the differential graded algebra of cochains. Yeah. Right.
Exactly. Yeah. Thanks for correcting this. Let me just. So.
And before you go on, I mean, I don't know if I should say something or not. So the whole point is, back in 2006. I wrote extensively on this and gave all these operations in the algebraic model, including the coproduct. So this goes back to 2006, even before Gorensky here in Ingson. And about 2 years ago, I wrote a paper saying that actually covers the geometric construction they do. So I think that if you have these things, and you're even talking somewhere where I'm present, then maybe, in any case, you should cite that. You should. I'll send you the references. You should cite that and look at it.
This is in the simply connected case.
This is in the Frobenius case. So this is the action for the Hochschild cochain model. What Manuel was just saying. So this is a general action in this case, and I gave an action of the Sullivan part of that action is the coproduct. I have the compatibilities and
Great. Yeah. Thanks. Yeah. Sorry, I wasn't aware. Okay. Yeah. So maybe then I should remove these people and say Kaufman.
you can decide whoever. Yeah, sure. Kaufman is correct, but you can keep Naef Willwacher there. I mean, I'm not saying you should strike them.
Yeah.
If you have a list, that should be included.
Right. Yeah. So basically, originally, yeah, it was, as far as I was aware, it was defined by Traylor and Zinalian, this BB structure on a maybe a cultural cohomology of a commutative Frobenius algebra. And I guess Ralph Kaufman proved that it coincides with the geometric one that comes from intersection theory.
Yeah, I was just about, before Ralph said something, I wanted to say a similar comment. Ralph did one of the first people who worked on the algebraic side of the string topology operations and structure of Hochschild. I don't remember the years, but we were kind of the works were done around the same time, so you can check the dates and see.
I see. Yeah. Okay.
Yeah, and Mahmoud, you can remind me. Did you actually look at the coproduct, or because you sort of had this operator structure? I'm not sure. Did you have the sort of the prop structure yet?
Who?
You.
We did. Yes, we did. We had the structure of the these chord diagrams, so they included some of the compactified operations as well.
Yeah.
Right. So then you also had the coproduct.
You can deduce the coproduct from those diagrams. I remember checking this.
Yeah. It included a lot of compactified operations back then too.
I see.
Anyway,
okay. Yeah. Good to know. Okay. Right. Yeah. So now, okay. So you have these operations, and let me explain where they come from algebraically. So you have these, again, kind of Gersten-Haber structure. So you can look at a topological field theory in 2 dimensions. And by that, I mean a functor from 2-dimensional cobordisms to vector spaces, a symmetric monadic functor. And then it's well known that such a functor is the same as a commutative Frobenius structure on the vector space that you attach to the circle. You can also look at variants of this setup where you impose certain conditions on your cobordisms. So you might ask your cobordisms to have non-empty outgoing boundaries. So for instance, you don't allow a disk which goes from a circle into nothing. Such a disk in this theorem above, which relates commutative Frobenius algebras to TFTs, corresponds to a co-unit. So basically what you get in this non-compact version of a TFT is a commutative Frobenius algebra without a co-unit. And the claim is that homology of the free loop space has such a structure. So this is due to Cohen and Gaudin. It's a commutative Frobenius algebra without a co-unit, or if you like, a non-compact or positive boundary 2D TFT. And so later there were several works of extending it in various directions. So one direction you can extend it to is extended to chain level. And the other direction is to allow surfaces with boundary. And also that there are several formalisms for TFTs with boundaries. So that there are basically 2 formalisms. Yeah, probably there are 2 formalisms for TFTs with boundaries. So there's a notion of an open closed TFT, which I guess goes back to Moore and Siegel, and an extended TFT, going back to Bias and Dolan. in the setting of open-closed TFT, so there was a construction of Gaudin again of an open-closed TFT underlying string topology, where the set of allowed boundaries, so you look at cobordisms, and the endpoints correspond to allowed to lie on submanifolds of them, but for Gaudin's version is just the manifold itself. So there's a single kind of boundary condition you can have. There's also some kind of an overview paper by Bloomberg, Cohen, and Telemann that there's supposed to be a chain version of everything, and submanifold, any submanifold should give you operations. And then also in Lurie's paper on the cobordism hypothesis, he also briefly remarked that using the cobordism hypothesis, you can construct the chain level extended TFT. And here the boundary conditions are even more general than submanifolds. They're arbitrary local systems on M, or chain complexes of local systems on M.
I'll make the same comment. So the open close. I mean, I in these social action papers, I extended it, and then I did the open closed bit also. I don't know, 20 years ago, 15 years ago, and then also Mahmoud Tradan Sanarian also did an open closed thing. And
this is before Gaudin, or
yeah, I don't even know what paper you're referring to. I don't know if it's published, but I mean, let's see. I can still check when my paper is, and okay. Mahmoud will know when his paper was. So let's see the open closed. Open closed is published in 2010.
An archive Gaudin's paper is 2008, I think.
Yeah, I mean, I can look at the archive, but
Gaudin did it in the topological setting entirely, and
right, and we did it in
and Thomas did it algebraically, which would
right.
You know, if you feed in like the cochains on the space into that machinery would.
Yeah, indeed. I'm only talking about the both of them are geometric versions.
Yeah, exactly. And Lurie's I don't remember, but if I remember, at least the original versions required that you have a fully dualizable object.
Yeah, I'll be talking about literally that.
Yeah, that corresponds to
the actions paper is 09, and before that there was a paper with Bob Penner on how this works in 06. So, but I mean, it doesn't. The dates are important, but I'm not sure. Actually, the Gaudin papers usually there was always some mistake in Gaudin's papers because all these structures were zero. So are you sure that they're not zero? Because she somehow always made, oh, this is just about the, what is this? I'm not confused. I'm confused because all the higher operations of Gaudin are zero. So the only thing that they recovered is the thing you get from just the usual TFT, and then you have the open closed TFT, which is sort of just a pi zero if you want what you want. And that, goes back to Cardi and Lavelle and those axioms. So I'm not sure what you're referring to there.
Okay, yeah, I'll discuss the extended TFT approach, and then I'll also mention this fact that, yeah, the fact that you just said that higher operations are all zero.
Right. I mean, but we have so both Clement and I we have higher version operations which actually work. And there are intricate equations that you have to solve, which are sort of interesting about these systems. So that's what's in this open closed paper. I mean, actually, Sullivan writes about this too in his review, so it's not unknown. I'm not telling you something that's not known.
Right. Okay, but yeah, let me move on.
Go on, please. Sorry.
So let me. So I'm going to be working in the setting of cobordism hypothesis of Lurie. So basically, you work with extended bordisms, and you're working with the 2 category of extended bordisms, or maybe infinity 2 category. And also, instead of oriented, I'll be working with framed bordisms. So objects of this 2 category will be points. 1 morphisms will be 1-dimensional bordisms, and then 2 morphisms will be 2-dimensional bordisms between 1-dimensional bordisms. And here I'm talking about framed version. So every bordism is equipped with a 2 framing, which means a trivialization of the tangent bundle plus a trivial line bundle on level 1 morphisms. Okay, so that's one semantic model infinity 2 category, and then the other one is just the 2 category of DG categories, or maybe presentable DG categories. And then for DG categories, there are 2 kind of finiteness assumptions you can consider. One of them is called properness. So DG category is proper if whenever you look at the Hom space between 2 objects. So this is going to be some chain complex, and you want this chain complex to be to have bounded cohomology, and in each degree it's finite dimensional. So that's what's called proper. There's also a notion of a smooth DG category, which I will need, but I will not define that. So again, it's going to be some finiteness condition, but of a different kind. And so that there are, again, 2 versions of the cobordism hypothesis. There's the usual one and the non-compact one, which again are parallel to this classification of 2D TFTs in terms of commutative Frobenius algebras and commutative Frobenius algebras without counit. Okay, so the first version is if you look at frame 2D TFT, so functor from 2 bordisms to DG categories. These are the same as smooth and proper DG categories. So basically, whatever you attach to the point, this allows you to reconstruct the category once you know some finiteness condition. So this is extremely powerful. Again, the main point is that you need a DG category and you need to check some finiteness conditions. And then there's this non-compact version, which again is completely parallel to the version I talked about before. So you look at 2 bordisms which have non-empty outgoing boundary. In this case, you can drop this properness assumption and just look at smooth DG categories. Okay, but of course you'll have fewer operations just because you don't allow all kind of bordisms. And now here's the main example of a smooth DG category. Let's say you have a topological space and you look at the DG category of chain complexes of local systems on the topological space. So this is a nice presentable DG category. And then if you assume a certain finiteness condition on this topological space, so what's called finitely dominated space, or which is by definition a retract of a finite CW complex, then this DG category is actually smooth. So for instance, if you have something that is homotopy to a finite CW complex, then you get a smooth DG category. And so, which means that by the coordinates hypothesis, whenever you have a finitely dominated topological space, you get a 2D TFT. Okay, so I want to call this the string topology TFT, and basically the rest of the talk will be about explaining why I call it that way.
Could you say a little bit about how you mentioned about this category, that it's nicely presented, and just can you say a little bit about how you think about this category and what its nice property is? Yeah. So so this DG category is just all kind arbitrary chain complexes. So the word presentable just roughly means it has all colimits. Smoothness is a certain finiteness condition. Yeah. But there's no constraint about the length of the chain complexes. They're not bounded in either direction. There's no boundedness assumed here.
Yeah, that's why I'm working with presentable DG categories. Indeed, in this setting, I'm not assuming any boundedness on the amplitude of the chain complexes. But what is important is finiteness on the topological manifold itself, or on the topological space itself.
And these are local systems of what?
Of just, let's say you work over a field, or maybe over the integers.
So just chain complexes of vector spaces or chain complexes of abelian groups.
And these are finitely generated abelian groups or not even?
No fineness assumption there.
Okay, thanks.
Yeah, I'm cheating a little bit in the definition of properness in the setting. So here, or not cheating, but didn't say it precisely, for any x and y which are compact, which again is a certain fineness assumption. But let me not talk about that, or maybe if you want, I can answer during the comments.
May I just ask a quick question? How much do you depend on this theorem?
So
is this motivation, or because you know why I'm asking? Because I'm not quite sure what the current status is as theorem goes.
So this is more motivation. Okay. Basically, what I'm going to be talking about next is how to actually compute it.
Okay.
So this theorem tells you that if I give you any Bordism, you can actually compute some invariance out of that, and it doesn't depend on how you decompose the Bordism.
Okay.
And what I'm going to do is I'm going to just decompose it and not care about invariance under different decompositions.
Well, can you equivalently work with the chains on the base loop space?
Yeah. So this category is always equivalent to modules over chains on the base loop space. Thanks.
Which is smooth as a DG algebra, assuming F has this finiteness condition, right?
Exactly. Yeah. Yes. Yeah, so there's again the notion of a smoothness for DG algebras, which is something about the diagonal bimodule, and yeah, under this fineness condition, this is a smooth DG algebra. Right. And maybe if you're not familiar with this, this corresponds between local systems and modules over chains on the base loop space. It has just more basic version, which is ordinary local systems, non-DG, are the same as representations of the fundamental group. So chains on the base loop space is kind of a homotopy version of the group algebra of the fundamental group. Okay, so now let's compute something. All right, so first of all, I want to compute the value on the circle and operations I get on the circle. So here I'm talking about the framed TFT. So there are different kinds of framings on the circle. So here I'm talking about two framings. So trivialization of the tangent bundle plus a trivial line bundle. And there's a Z worth of framings. So I'll denote them by S1n for some n. And basically all of them, let's maybe assume that M is actually oriented. All of them are just given by homology of the free loop space, possibly up to some shifts. Okay, and then in the TFT, again, the basic operation is the pair of pairs product. So you just look at two circles and then you can combine them, which is drawn on the right. Well, the theorem is, the proof is that it actually coincides with the string product. So again, the theorem is about the TFT that I just defined above using the cobordism hypothesis. So you plug in just the homotopy type, M, and look at the category of local systems and compute what you would get in TFT. The way you compute that is you have to decompose this Bordism into elementary pieces. Maybe you group them with Morse functions, and then you have a single critical point. So I've drawn it on the left, and then you know what you attach to all elementary pieces, and then you just compose it back into Bordism. That's your answer.
Pavel, so you're working with non-equivariant homology here, right? So you probably mean loop product, right?
So, yeah, right. Yeah. So
Okay, good. Yeah.
Of course, the TFT kind of sees all the information, but here, yeah, indeed, we are computing the loop product. Okay, so let me make a slight digression on Euler classes. This will be important, again, for the string coproduct. Already I'm motivated with derived cobracket, so there are two versions of the derived cobracket, one with the trivialization of the Euler class, one without the trivialization of the Euler class. The same thing for the string topology operations. And now I want to do the same in this kind of homotopy world. So let's say, again, you have this finally dominated space as before. So you have the projection map and projection map pi from the free loop space to X. Then you can consider the following three kinds of characteristic classes associated to X. And I'm starting from the simplest one and going to the most complicated one. So the simplest one is just the Euler characteristic, and it's a number. But you can also lift the Euler characteristic to a zero chain on X. So there's a canonical zero chain on X. And this zero chain is just Poincare dual to the usual Euler class in top homology. If you push forward the zero chain to the point, you just get the Euler characteristic. So this is a kind of refinement of the usual Euler characteristic. Okay, so this is the second level, and finally you can lift it all the way to the loop space. So there's kind of a loop version of the Euler class, and this is a zero chain on the loop space now. And again, if you push it forward to X, you recover this Euler class on X, and if you push it forward all the way to the point, you get the Euler characteristic. Okay, so there are these three levels of the Euler characteristic. Let me relate to something rather classical, which is called Wall's finiteness abstraction. So Wall basically answered the following question. Suppose you have a finitely dominated space, so space which is dominated by a finite CW complex. Is it actually homotopy equivalent to a finite CW complex? And then he constructed a certain class in reduced K theory of the group algebra of the fundamental group. And this class vanishes if and only if X is homotopy equivalent to a finite CW complex. And so this loop Euler class is a closed, it's closely related to this Wall's finiteness abstraction. Okay, so now let's consider another map, which is inclusion of constant loops, X into Lx. And then you can ask, well, can I lift further this loops, the loop Euler class to X? Or in other words, can I trivialize this loop Euler class in a relative homology, Lx relative to X? And this trivialization is the same as trivialization of Wall's finiteness abstraction, essentially.
Is this loop Euler class is in the zeroth equivariant homology or ordinary?
Yeah, it lifts to equivariant homology. It actually lifts all the way to A theory, if you like. Yeah, so there are a lot of compatibilities that I'm not writing.
And is it like trace of holonomy? Is it that?
It's, yeah, I'm not sure I know such an interpretation, but it's the same idea.
Okay. There's a Chern character has a similar property. It's called the Bismuth Chern character, and that becomes trace of holonomy.
Yeah, so this is the Chern character for local systems. There's a, yeah, it's essentially the Chern character of the trivial local system. Yeah. Okay, and so there are two kinds of trivializations of this Wall's finiteness abstraction you can construct. There's kind of one which is about manifolds, and there's one which is something quite fancy for general topological spaces. So if you have a compact Euclidean neighborhood retract, then going back to the work of Walthausen and more recently Dwyer-Wiles and Williams, they've constructed a canonical trivialization of the Walsh-Minus abstraction, or a canonical lift, or canonical homotopy between I of the Euler class on X and the loop Euler class. And this kind of bounding chain that they construct is homomorphism invariant. And another one, which comes from intersection theory, so you have to write a specific model of Petrarchan tone collapse for, in the case of a smooth manifold, then you can construct possibly a different bounding chain. And this one uses the smooth manifold structure, so this is going to be diffeomorphism invariant. Maybe in 5 minutes, I will say that actually the first bounding chain I said is homomorphism invariant, but it's actually known to be non-homotopy invariant. And this will be important. Okay, so, all right, so basically, okay, so there are these Euler classes, different versions, and that's what you should get out of the slide. Now let me go back to string topology operations. So I want to explain how one can get a string coproduct out of TFT, out of this extended TFT that I've just constructed. And basically, if you look at a pair of pans, which is upside down, so one circle splitting into two circles, you can basically play the following trick. You take one circle and pull it down, and you get a picture on the left. And the way the picture on the left looks like, it's a multiplication followed, and then you apply it to the elbow. And you can also do this on the other side. You can split the others, pull the other circle down, and extract an elbow. This is one way to actually prove that these string topology operations on the non-chain level in higher genus, or for instance, this kind of coproduct one are actually trivial, is to draw these kind of pictures. But if you look at it algebraically, what this is saying is that, okay, if you have some kind of coproduct in the middle, on the left, you have multiplication into coproduct applied to the unit. And on the other side, again, you have coproduct of the unit and you multiply it on the other factor. Okay. Okay, so why is this useful? So let's look at the elbow and let's look what the TFT attaches to that. So this is actually a relatively easy computation. To the elbow, you actually attach this loop Euler class. So the loop Euler class is a zero chain of the loop space. You push it forward on a diagonal map to Lx cross Lx, and that's the value of the elbow. Okay. So now suppose you have, and so far this is just works for any homotopy type, for any finitely dominated homotopy type. Now let's suppose you have one of those bounding chains that I just talked about. That means that you can lift this from this elbow from the loop space to X itself. And what this means is that this allows you to get a secondary operation on the relative loops. So again, the story is completely parallel to what I described before. If you have a trivialization of the loop Euler class, you get, this is going to be a homotopy from 0 to 0. So this is going to be a secondary operation on the homology of the loop space. Or if you have this lift of the loop Euler class, you get an operation on the relative homology. Okay, so you have these two operations, and one of the main theorems is that these two operations actually recover the geometric string coproduct. obtained using intersection theory. Okay. So when I say it recovers the string coproduct, again, I gave you two kinds of bonding chains in the second case. And you have to use the one that comes from intersection theory, obviously, to get the string coproduct coming from intersection theory.
Pavel, can I ask a question? When you say recovers the string coproduct, you're showing, you're claiming they are equivalent in homology.
Yeah, yeah.
Okay. How about
operations?
Yeah. How about chain level?
Well, what the proof does, it constructs. So these operations in the TFT, they're defined on chain level. What the proof shows is that they're chain homotopic.
Okay, but that does not mean they're equivalent as maybe A infinity coalgebras or whatever.
Oh no, we're not considering. No, we're not considering like associativity of these operations or anything like that.
Okay.
Indeed. Yeah, is it just like for the actual operations? Okay, so let me say a few words about homotopy-invariance. So as I said, the input to this 2D TFT was just a homotopy type with some fineness condition. So so this 2D TFT is completely homotopy-invariant. So anything you can extract out of this 2D TFT will be homotopy-invariant by construction. So for instance, once you know that the pair of Pans products in the TFT is the string product, you get this theorem due to many people that the string product is homotopy-invariant. So if you have a homotopy equivalence of closely oriented manifolds, then it intertwines string products. Okay, now let's look at what happens with the string coproduct. So the way I define the string coproduct, I need a little bit more than the TFT. I need the TFT and this bounding chain, which related the loop Euler class and the Euler class on X. The TFT part is completely homotopy-invariant, so the only homotopy non-invariance might come from this bounding chain. So you need to know what happens to this bounding chain under homotopy equivalence. Okay, so let me recall, again, something rather classical. If you have two CW complexes and you look at, you have a homotopy equivalence of two finite CW complexes, then Whitehead introduced this notion of Whitehead torsion. So it's usually in some group related to K theory, but you can push it forward to homology of the loop space. So basically, the Whitehead torsion will be a class in H1 of the loop space relative to constant loops.
Question, yeah. Is this trivial if X1 and X2 are simply connected?
Yeah, yeah.
Good.
Thanks. Yeah, so indeed, this torsion and all questions about homotopy-invariance are about the non-simply connected case. This Walls fineness substruction depends on the fundamental group. Whitehead torsion depends on the fundamental group. And as an example, which goes back to Reidemeister, so that there are two homotopy equivalent length spaces, L71 and L72, but they're not homeomorphic. So there's a homotopy equivalence between them, which has a non-zero Whitehead torsion. Okay. And it's known that if you look at this Dwyer-Williams bonding chain, that one is not homotopy-invariant, and more or less by construction, it changes by the Whitehead torsion. So what this means is that, again, the Whitehead, the string coproduct, if you use this bounding chain, will also not be homotopy-invariant, and it will change by the same Whitehead torsion. So Florian has computed some examples in the case of the length space L7K, and he checked that that seems to be true, that if you look at the usual intersection product computing as a usual string coproduct computed using intersection theory, that one has the same failure to be homotopy-invariant. Basically, it sees this torsion information. Okay. And maybe just to say quick few last words. So here I started with a 2D TFT with a little bit of an extra structure. So something about this elbow. So I have to trivialize this elbow to get new operations. And you can apply this to other kinds of 2D TFTs. So for instance, you can work with the A model or for the B model, with the B model. In the case of the A model, actually, the example I'm talking about is an example of an A model, just because if you look at a spin manifold, then the wrapped Foucault category of cotangent bundle is going to be equivalent to local systems. So the A model in the cotangent bundle is essentially this string topology TFT. And this allows you to define string bracket for symplectic manifolds. And then, yeah, you can do this for the B model, or basically whenever you have a smooth DG algebra, you can work with that, and you can do it for free algebras. So, okay. Yeah, so I'll stop here. Thanks.
Okay.
So let's give a virtual clap for Pavel. Thank you.
I'm not even muted. I can't do that.
So,
or I can knock.
Are there any questions that you want to be part of the video, the recorded video?
I have a question, but I don't mind either way. Yeah.
Okay.
If you,
yeah. Any questions? I will stop the video and have a second session for questions as well.
yeah, just a general question. So, about this A model thing. Why is that local? Usually an A model has instantons.
Well, so first of all, this is an exact manifold. So you look at a cotangent bundle.
Okay.
Yeah, and the claim is that basically, if you look at this wrapped Foucault category, you look at any point and you look at cotangent fiber as a Lagrangian, that cotangent fiber, first of all, generates the category.
Okay.
And second, obviously, it computed endomorphisms of the cotangent fiber. Yeah. And that's just changed on the base loop space.
Okay, okay, so that's your locality. Okay, so you that way you kill the instantons. That makes sense. Otherwise, you don't get the local, right?
May I ask a question? So in going back to those to the surfaces where you chose this non-vanishing vector field, when you say homotopy class of curves, are they being homotopes through a family of such curves or arbitrary family of such curves?
Such meaning?
Such meaning winding number 0.
No, yeah, that's the point. So you look at homotopy classes of maps, of loops, and basically to kill this problem, you find a representative which has a winding number 0. You compute this delta on that representative, and then this problem with Reiter-Master 1 move goes away.
Okay, I understand. And okay, and then this interpretation of winding number only is 2-dimensional. So you're saying there's a similar thing, or is it n-dimensional?
The vector. Yeah. So if you have a vector field on a higher dimensional manifold, it still will trivialize the Euler class. So I don't quite know the geometric interpretation of the string coproduct when you have a trivialization of the Euler class using vector fields.
So which representative do you choose then?
Yeah, so again, I'm not quite sure, but the idea is that the string coproduct, if you look at this picture, yeah, so if you look at this picture, you have this kind of interval worth of operations, and at the endpoints you get something about the usual Euler class.
Okay.
So once you trivialize that Euler class, you get an honest operation. Or if you pass to relative homology, that also goes away.
I just wanted to make one comment, the separate comment. There was a student of Dennis's, Samnath. I forget what's the last name, Manuel?
Basu, yeah.
Samnath Basu.
I was going to mention this.
Also works, he also showed string topology in some senses, non-homotopy invariant. So but I don't know how it fits into your setting.
It should fit, but it's different. Yeah, I can say something about that later. Okay, I'm going to